So I want to start with reminding notation. So reminds that we have a curve x, which is presented as a projective curve, non-singular, minus finite set S. And this set S has distinguished point, so it's in particular non-empty, S0. And we also have a vector in tangent space at this specific point to x bar, which is a non-zero vector. All this is defined, curve is defined over F, and everything is defined over F. F is a sum field. Now, notation which I'm going to use is Cli. I'm going to introduce again, so Cli x. This is a coalgebra, and it's defined as follows. So it's a cyclic tensor algebra of associate graded for the weight filtration of H1 of this curve x, divided by a certain subspace, which I last time didn't want to talk about, and also not going to talk right now, shuffle relations. I mean, I defined it last time, but didn't explain anything about this. So just some subspace of shuffle relations, and twisted by Tate by 1. So this is a Lie coalgebra. Okay. Now, what I really need is a Lie algebra. So I called Cli x. So this is by definition the dual to the previous guy. And it sits, so first of all, it's a Lie algebra. And the main fact about this Lie algebra that this Cli x maps and actually isomorphic to special derivations. So we have the fundamental group. Now I write Motivic, but you can think that I'm talking about pro-nilpotent completion, for example. So we write pi 1 of x with this tangential base point. And then I take the associate graded for the weight filtration. And after this, this is a very clear object. This is just a tensor algebra of H1. So there is nothing to worry about. And so it maps to the derivations of this Lie algebra. And these derivations are special. So that's why we care about this Lie algebra, derivation Cli x. So I remind you that this is free Lie algebra generated by H1, by gr WH1. Okay, so what was the goal of the story? So the goal of the story was to define this correlator. So I can put it this way. So I have this Lie algebra Cli x, and I wanted to take Lie algebra of the Hodge-Galois group. I'm going to define Hodge-Galois group in a minute. So I just want to motivate why I'm going to talk this order, not the other. This is a Lie algebra. Lie algebra of the Hodge-Galois group of the category of mixed Hodge structures over R, which I'll talk about in a second. So I want to construct explicitly a map like that. And its main point is there is another guy which I didn't define, Motivic Lie algebra. And so it's supposed to go like that if F sits in C. So we are not going to talk about this at all today. So we're going to concentrate on construction of this map. Now, yeah. No, not yet. So I will say in a second. So I'm going to construct a map of the Lie of the unipotent, which is GM C2R equivariant. But I'll say this in a second. I didn't define what this is. So so if I dualize this construction, I will explain that this is this Hodge correlators I'm talking about. But now, after having said this, I'm going to remind you the story about Tanakian formalism for mixed Hodge structures. So it's quite well known, but still. So first of all, so I need this in order to define this guy, to explain how this guy looks like. So that's the first question. So first of all, there is a definition due to Deligne of a mixed real Hodge structure. And so it's the following data. So first of all, we have V, a vector space over reals. Then you have W. It's increasing filtration, so it's a weight filtration of this vector space over reals. And then there is another filtration, decreasing, descending. The Hodge filtration. And now it's filtration of the complexification of the space. That's a standard definition. Now, the main point is that, as was proved by Deligne, this category. So we have a category. How I don't know this, mixed Hodge structures over R, and this category is abelian. And obviously tensor has duals, so it's a nice category. But in particular, it's abelian. And there is a fiber functor. It's not obvious from the definition, it's abelian. Not at all. So there's a fiber functor.
So it's not any,
Huh?
it's not any collection of data like that. It has to satisfy some axiom.
Oh. sorry. Such that, I beg your pardon, such that if you take GR with respect to W of this complexified vector space, then this is direct sum of pure Hodge structures. Or more precisely, you can just say that this is direct sum, if you take Wn, P plus Q equals N of F P F Q bar. Okay? That's the only condition we have. I beg your pardon, I was about to forget to say this. So, so there's a fiber functor, which Hodge fiber functor, which takes us from the category of mixed Hodge structures over R to the category of real vector spaces. Actually, there are two functors. The first one, not this one, is just take the underlying vector space. But I want the other one, which takes mixed Hodge structure and associate to this another vector space, which is just associate of the original V by the weight filtration. So this is, it has a grading, but this is just a vector space, nothing else at the moment. So now by definition, the Hodge-Galois group, the R Hodge-Galois group, it's an algebraic group over Q given by automorphisms of this canonical fiber functor, which respects the tensor structure. Okay, so now why it's important? It's because of the Tanakian formalism. We know that this functor, omega Hodge, it's a functor, as I said, from the category of mixed Hodge structures, real mixed Hodge structures, to the category of G Hodge models. I tend to forget this R here. I'm consider real Hodge structures, so I put R whenever I didn't forget it. So and this, so why this is so? Because we have a guy here. We assign to this the value of this functor, but then this group acts on this guy, and so we get G Hodge model, And this is a canonical equivalence of categories. Okay, so now the category of mixed structures has a little bit more of data. There are two canonical functors. First of all, respecting the fiber functor. That's important. So first of all, we have a functor GR W, which takes us from mixed Hodge structures over R to just Hodge structures. I mean, direct sum of pure Hodge structures, which by abuse notation we call pure Hodge structures over R. And on the other hand, we have the functor back, which takes a Hodge structure and considered as a mixed Hodge structure. Now, because the fiber functor is compatible with that, so first of all, we notice that if you take the composition, goes this way, so you get identity. And therefore, on the level of the groups, we have the following thing. So we have projection. First of all, we have embedding of group GM C to R to this G Hodge. So why do we have this embedding? Because we have a functor from big category from mixed category to smaller category to pure category. Now this pure category is equivalent to this GM C to R. This is just group GM considered with restricted scalars. Models. And so because we have functors this way, so afterwards these groups map the other way. Okay. Now we have the functor in the other direction, and therefore we have a projection from G Hodge to this GM C mod R. And therefore we get extension. That's where I'm heading. So we said that U Hodge is just the kernel of this map P projection, and so we have exact sequence and what is important that this exact sequence is split canonically by this map S. So now we have we concentrate on this unipotent tail, unipotent radical of this group, and we can just say that this Lie U Hodge unipotent radical is a free Lie algebra. It's a statement in the tensor category of real Hodge structures. So the first observation is that, of course, it's itself a Hodge structure, mixed Hodge structure, pure Hodge structure, sorry, because the group S of GM, C over R, X here, so it's by definition a pure Hodge structure. But it also, I mean, X, I tend to, okay, so text, but I need to take the Lie algebra. So I was it text, it's okay, but what I really need that the S of GM C mod R acts on this Lie algebra, so it's a Hodge structure. And it's Lie algebras, and it's actually commutator is compatible, so it's a Lie algebra in the tensor category of Hodge structures. And it's a free Lie algebra because there's no x2 and higher in this category. Okay, so now we know a little more about this, which is the main point of me talking about this right now. So this is a free Lie algebra in the category of pure Hoy structures. But we can just look at this just as a Lie algebra. And I just take Lie U hot tensor C over R. And so this Lie algebra has generators, so Deline's generators. So we can call them dpq. So here P, how I call is bigger or 1 and Q is bigger or 1. And they satisfy the relations that dpq bar is minus dqp. Otherwise, there is no relation. So what I said before, that's free in the category of Hoy structures, implies that it should have some generators. And Deligne constructed some generators. And so you can just say now that what is a Hoy structure? So and real mixed Hoy structure is the following data. So you have a vector space such that its complexification is bigraded. This is just to say that we have a direct sum of pure I don't put C here, Hoy structures. And then there is there are operators, these operators Dij, let me call them dst, which belongs to endomorphisms of this bigraded guy. And the main point is that the degree of this dst is minus s minus t. So this operator d, it shifts degree by minus s minus t. Okay? So I'm not going to tell you how these operators were constructed for the following reason. So first of all, if you think about the Lie algebra which has generators, this is something which you think never happened because it's a free Lie algebra. Why it should have any canonical generators? Because if you have one set of generators, you can immediately cook up some other set of generators. So what are we talking about here? Now, it turns out that this situation is better than usual situations, that there are canonical generators, but in what sense they are canonical, you can see only in the family. So if I'm not in a family, I have a trouble saying that these generators or the other generators are better than any other set of generators. And so it turns out, and so we will see this a bit, maybe like an hour later, that this Lie algebra has a different set of generators. So I call them green operators, which are really different. So they express through one set expressed through the other as a little complicated kind of polynomial equations. So those other generators, so the key fact of life, key for us, there exist other generators. So I call them green operators. So let's call them GPQ. They parameterize by the same data. And have the same reality condition as those ones, which behave nicely in families. Now, what does it mean behave nicely in families? What exactly are we talking about here? So if you have a just mixed Hoy structure, you can use this operator to construct a period of this Hoy structure. Just take matrix coefficients of these operators. Choose some basis, so you get some functions. And so the question is how to determine what kind of conditions the fact that you have a variation of Hoy structures impose on these functions. And so as far as these other operators are more natural and in fact canonical because they satisfy a very simple Maurer-Cartan type of equations, which is just it's nonlinear set of equations but quadratic. And using this equation and explicitly how you get from one to the others, you can theoretically write down equations of those generators, but they're quite complicated, actually. I don't think anybody wrote them out. So for that reason. OK, so the message, I repeat again, the message is that there are canonical generators here. It's a little unusual situation, which behave nicely in families. And now we return back. Yes?
Is there one of these set of generators sort of related to x between x X1 between the trivial Hodge structure and the...
Exactly.
Which one?
Okay, let me write it down. So, so this is excellent point. The Lie of U Hodge R is generated by in the tensor category of Hodge structures. Is it still visible when I write here, or I should avoid this? Richard, this is your... Oh, no other complaints? Okay. Okay, so it's generated in the category of Hodge structures by the following guy. So you take direct sum over all isomorphism classes of your Hodge structures, of whom? So you take X1 in the category of mixed Hodge structures over R between R of 0 and your test Hodge structure H, dualizes, and tensor over endomorphisms of H, which is, in this case, is non-trivial. It's not R, could be not R, could be C, with this H. So this is a huge object in the category of pure Hodge structures. It's just direct. So just remind you that pure Hodge structures which have non-trivial X groups are exactly the ones which parameterized by a pair of integers P and Q, such that P and Q big or equal to 1. And so for each of such objects, so okay, so just write it down. That irreducible objects of this category of Hodge structures of R, I don't know how you call them, HPQ, they parameterized by integers P and Q big or equal to 1 up to symmetry. So just pair of integers big or equal to 1. And they have the Hodge weights minus P minus Q and minus Q minus P. If they're different, if they're the same, they're just minus P minus P. So this is a list of the simple elements in this category with non-trivial X1s. And if you take X1 tensor this element, this object of this category, then you get a huge object in your category, and your Lie algebra is generated by this object. Okay? That's the answer to your question.
This is related to the D's or the G's?
It's related to both, but the main point is that if you have, let's say you have nilpotent Lie algebra, so how you think about is generators or cogenerators. So you take first dimensional homology, if you cogenerate cohomology. This is, so if you talk about generators, then you have a vector space, it's some subquotient of something, but this vector space doesn't sit in your Lie algebra. This is the main point here. So this, yes?
If instead of structure one look at the Simpson twisters, and one has mixed Simpson twister also,
Yes.
then one has just the same story, so U is the same.
Yes.
But there one can have a natural set of generator by imposing some PGL2 invariants. Do you know if it is the same as one or the other?
Another set of just repeat.
Then one has a group PGL2
Yes.
acting naturally,
Yes.
and there is for Simpson one sort of generator for which they come by representation of PGL2, and this characterizes it uniquely.
Not sure at least. We will see. I will also have C2 Swiss twister plane in a little later, and GL2 and so on, but I'm not sure this is the same. So did I finish with this point? Is that okay to move on? Okay. Okay. You have a question, Richard?
And for what you wrote there, I think what is canonical is that Lie Medabelian is canonically isomorphic to the same.
Yes. H1, which means Lie Medabelian, is canonically identified with this, but there is no way to pull back Lie Medabelian to Lie. Yes. So that's the main point which you make here. But in spite of this fact, it turns out that there is a way. I mean, you can call any lift your canonical favorite lift, but there is only one which satisfies the simplest differential equations. All right? Yeah.
Where does the inequalities on P and Q
You have to calculate X1 between real Hodge structure, and first of all, you have to say who is HPQ. So this is a two-dimensional vector space with a mixed Hodge structure. Then you have to calculate X1 between R of 0 and HPQ. And as a result of calculation, you will see that X groups will be 0 unless the weights are minus P minus Q minus P, where P and Q are big or equal to 0. That's where the inequalities come from. Okay? This basically, this line explains these inequalities here. All right. So I stop here for a while because we are going to see the same in the Motivic level later. And I just want to, at least this picture where it's clear to be understood. So, OK. So now we have, I want to construct a map of Lie algebra to some other Lie algebra. This Lie algebra is kind of given to us. This Lie algebra, if I assume that I have some generators, I can just define this map on the generators. And then this is exactly, the claim is that this is exactly Hodge correlators. Precisely, so to define a map, for each P and Q, I have to define a map from here to here. And this map is equivariant with respect to the action of their the C star, the GM C2R. And therefore, all I need to do, oh, that's nice. So I just need to construct one map. So this is this Hodge correlator map, which is a map from C Lie star. So I have to dualize X to, I can kind of put it to real numbers. But what I'm really doing, so I'm taking here C Lie X star, and I consider here component of degree P minus P degree PQ. And so this goes to this vector space, which is generated by the dual to this PQ. So to construct a map from one dimension, basically, it's not exactly, but to construct a map from one-dimensional space to some other vector space is the same as to give a linear function on the dual. And so, therefore, the very existence of canonical generators means that to define this map to define the action, the map of Lie algebra of the Hodge-Galois group to this guy is the same thing as to construct a collection of linear maps, which you can just say this is a single linear map, because then you just decompose it by the weights. And that's exactly the map which I'm going to construct. Okay? So that's what I'm going to do right now. And I'm going to do this in families, so you will see that where the differential equation comes from. Okay? Once again, is that clear what I said? Because this whole speech about Hodge structures was made in order to say this. So,
no, it's not clear to me.
Okay, yeah, go ahead. So once again, so I have a map from the free Lie algebra to some other Lie algebra. So to construct such a map, if you have generators, is the same thing as to give this map on generators, which could be anything.
The image of the generator.
Yes.
Yeah.
So if you dualize this, so you have to have collection of linear maps from one-dimensional guy to your big guy. So if you dualize this, it's the same thing as to give yourself a collection of linear functionals on the dual space. Now I can take their sum if I wanted, because these linear functionals in any way will be bigraded by the weights, so I can distinguish their components in any case. This is a map. This guy is bigraded. And so whenever I produce a linear functional on this bigraded vector space, it automatically splits on the components. And so I'm going to produce one linear map, and it has, in the end of the day, and it has the properties I kind of I produce collection of these maps. Yeah.
I'm confused. I thought you wanted a whole series of linear maps.
It's the same thing. I'm saying that if you have, I want to have a collection of linear maps.
Yeah.
Okay. Now, what is the property of this linear map? Is just some element of dual to this guy.
Yeah.
Okay. Dual to this guy and dual to this guy, therefore, are bigraded. So this means that I want to have a collection of vectors in the original guy, or what is the same collection of linear functionals on this dual. Of given weights. For each P and Q, I'm going to construct one linear functional of weight PQ. Then I take the sum. I don't lose any information because just if I have a graded vector space and I have vectors which has given grading components, so considering their sum is the same as considering them component-wise. Okay?
Are you working with the Hodge realization of Seeley as opposed
Yes,
to
yes, definitely, yes. Beta realization. Is that okay now? Yeah. So that's why I'm going to construct either one linear map or collection of linear maps. It's actually will naturally come up as a collection of linear maps, but okay. Now let's do it. So once again, so my point was to explain that the problem which I'm solving in a second is a natural problem, and so it exists anyway. And so it exists just because of the fact that these canonical generators exist. And mixed Hodge structure exists in fundamental group. And finally, one more comment about the general setup. Where is the mixed Hodge structure? So what we're doing here, I just repeat that we have a map from Lee G Hodge. I really better write down U Hodge, which is equivalent with respect to the C star cross C star. Maps to this C Lee X. But now we know that this is the same as some kind of endomorphisms, derivatives with some special properties of the GR W pi 1 M X. Okay? So in the end of the day, we construct a map here. So we construct this map by using this Hodge correlator map, dual to it, and by using this this isomorphism, in particular this map kappa. I was talking half of the previous lecture, that this Lie algebra acts by derivations on this guy. Okay? So in the end of the day, we just get this. So we have a Lie algebra acting by endomorphisms of associate graded of some guy. And this is, to construct this map is the same thing, is to define a real mixed Hodge structure on pi 1 made nilpotent or Motivic of X. So this is why the construction I'm talking about is the construction of mixed Hodge structure. Okay? So it's a combination of two things, the Hodge correlator map and this action of the cyclic Lie algebra on associate grade. Yes, this is the one. Yeah. Yes, the series. This is the one we expect. Yes. Otherwise. All right. So now let's define it. So by now, I'm going to kind of different chapters. So if you, I kind of start from level 0, because all this knowledge I'm going to use maybe in half an hour, but not immediately. Okay. So Hodge correlators. But I'm saying again and again that I want to stress that the construction which will appear on the blackboard shortly answers certain questions which exist anyway. So first of all, we work in families. So I assume that I have a family of curves. It's a family of regular projected curves which we denote x sub b. B is element of your base. And we also have sections. This is my points. So Si is my set S. So we have points, and we have also tangential base vector in the family. And so now we can form C Lie X, this Lie algebra, but now it's a relative version. So this is a Lie algebra in the tensor category of variations of pure Hodge structures. Okay? So in particular, it has the following data. First of all, this cyclic Lie is a vector bundle. On B with Gauss-Manning connection which I call D. And secondly, if you take its complexification, is direct sum of its components as usual. So it's a bigraded thing, has Gauss-Manning connection, and in addition to this, the Gauss-Manning connection satisfies Griffith's condition, Griffith's transversality.
So when you take a vector number, you want to use infinity vector and not holomorphic.
Yes. It's a I mean, it's a local system. It's a local system with Gauss-Manning connection, so you can think about it. You can take flat sections, you can take infinity sections. It's up to us. Okay, so now what do you want to do? So now I take B and multiply this by C2. It's a twistor plane. It's a C2 with canonical coordinates. And so it naturally projects to B. That's a map pi. And so then I can just construct pullback of this silly guy to B cross C2. And I just want to say that it has flat connection, which I want to denote. So it's D, the original Gauss-Manning, plus differentiation on C2. So introduce this connection with this guy.
Sorry, I don't know what twistor.
It's C2.
Can you say where?
It's C2. It's just a plane with coordinates Z and W. There's, I mean, if I said twister, it doesn't yet has any content.
We'll see why it's here.
Hopefully, yes. So far, just C2 with so again, so this C2 is very important for me. This C2 just has canonical coordinates, so it's not a two-dimensional vector space. A two-dimensional vector space with a given coordinates, I can take 0.11 and so on. All right. So what is the goal? So we want to define a connection I call it nabla G on pi upper star silly x. Okay? But you can say that we already have a connection on this guy, which is just d plus dc square. And this means that my goal is the same thing as constructing difference between these two connections, which is a one form G, it's a green form, on B cross C2 with values in this Lie algebra C Lie X. And so for now, this is a goal. Okay? So how they are related? So the connection nabla G is just the original Gauss-Manning connection plus the trivial connection C2 plus this green form. Okay? So I want to construct G. Now, this G will have some properties. In order to stay this, you have a question?
You would say it was value C Lie, but I would expect a term of this of
No. It's values in P upper star C Lie X. Not it's values in Lie algebra. And it has some properties. I'll tell them in a second. In particular, it will be algebraic with respect to C2 directions. But before I say this, let me.
But to define the new connection, you by centerless, I guess, but it's the advanced action which you add.
Sorry, what?
To get if you have one connection and you want a new one, you need to add
One form.
one form with value in endomorphism, and so it's the add of.
I don't want to argue, but I construct. I'm going to construct connection with values here at x on itself.
Yes.
But okay. So you have C star cross C star acting on the following guys. It acts on C cross on this C square in the completely standard way, and it also acts on C Lie. Yeah.
You say precisely what's nabla G of a section, given section?
So if I use the fact that if I have two connections on the same vector bundle, they differ by differential one form with values in endomorphism of this vector bundle. Okay?
Uh-huh.
So I want to construct a connection, but I already have a connection. The Gauss-Manin trivial extended to C2.
Yes.
So this means that to construct any other new connection, all I need to do is to construct a one form with values in endomorphism of this bundle. Any two connections differ. If you take difference between two connections, it's a linear map from your bundle to your bundle tensor omega 1.
Yes.
And so I'm going to construct it. So it will be with values in C Lie x, but it acts on itself. So okay.
Yeah, I think I see that.
Hmm?
Yes. Okay.
So this explains how we get this G and how this G is going to be used. But in order to state its properties, so I wanted to note that this C star cross C star acts on C2, it acts here because we have bigrading. It was on the blackboard. And it also acts on the Dolbeault complex of any complex manifold. Just Dolbeault complex has bigrading, and having this bigrading just means that we have such a action of C star cross C star. And so having said this, I now can define what the properties of this connection is going to be. So that's a theorem. Any questions? Okay. So theorem A. This G is C star cross C star, and also cross sigma Galo C over R, which I'm going to ignore for almost of the time. It's a trivial addition to this. Invariant. It's a Galo C over R. It's a complex conjugation. And if I start talking about this, I have to say the sigma acts on C2 by the rule that ZW going to W bar, Z bar. So C2 comes as a real structure. So this is invariant, C star invariant one form with values in this guy, which is algebraic along C2. So I can just say that this G belongs to one form on B cross C star with coefficients P upper star C Lie x, which is C star cross sigma invariant. And now comes the main point. The main point is that the restriction of the connection nabla G to the B cross C given by the equation z plus w equal to 1 is flat. So I'm going to construct a connection, and this connection is flat when it's restricted to this line in C square plane. Okay?
What does algebraic along C2?
It's a connection, so it's a differential form with coefficients and something. But this differential form, when restricted to C2, is algebraic differential form. It's just the polynomials in Z and W and dV and dZ.
But somehow analytically depending on B.
And depending somehow C infinity on the rest of that. It will be true by construction. So it comes by construction this way. So first of all, a warning that this connection is not flat. It's not flat. And moreover, if you consider the curvature of this connection, this is a very important invariant of the data. So if you take the curvature of this connection, but curvature in the C2 direction. So here I mean the following. So my space B cross C2 is canonically split in the product of B and C2. And so the curvature of a connection is a two form. And what I want to do, I want to restrict this two form just in the C2 direction and see what do I get. And what I get is described as follows. We can write it down always as a sum of something, and then Z to S, W to T, then some coefficients, which kind of nuisance, but I write them down. Then dZ, dW, and most importantly, G. Okay. It's really not that important. It's a normalization coefficients. I just advise you not to pay too much attention to them. So the fact is this, that you restrict your, and the sum is over ST bigger or equal to 0. So whenever you restrict algebraic connection and to C2 and take it curvature, so its curvature being C star cross C star equivariant must be of this form. Because the operators G, S plus 1, T plus 1 has homogeneity minus S minus 1 minus T minus 1. And if you want to get anything C star cross C star invariant, you must have, and this is a two form, it's written this way, so you have no choice. Okay?
I think I'm confused why I don't see things like dZ bar, dW, and so on.
I did not define this connection, and this connection has non-trivial connection transport along the C2 plane. So this connection is a one form on B cross C2. And so it comes. It's holomorphic in the C2 direction. That's what I said. It's algebraic, or you can say holomorphic, the same thing, in the C2 direction. Therefore, if you take the curvature of this connection, you inevitably, it inevitably has this form. Okay?
I'm sorry, it's a property of the G is that this is going to be convergent, is it?
Sorry, what?
The sum over all ST?
It's a formal expression. So, I mean, it's actually a finite sum, so it doesn't make a big difference.
Okay. And why does it then vanish on Z plus W? Why does it vanish on Z plus W?
This is the main point. I'm not sure what can I say about this. So this condition is going to encode the differential equations on periods.
But are we going to see this here?
In a second, just a second. So I'm still talking about part one of this statement, that the form is C star cross C star equivariant, and I show that this condition tells us something. It tells us that the curvature of this connection comes this way, no matter what. And so this leaves in this C Li x minus S minus 1 minus T minus 1. Okay?
Why is it finite sum?
By construction. So, I mean, it's okay. So it's a formal sum. I better say this way. So if you take any particular construction, it's going to be finite sum. You can consider it as a formal combination. It's really not nothing important here. It's a formal combination. Huh?
Yes, whenever the algebra acts only some finite coefficient.
Yes. For example.
because of the coefficient pi star.
You can say that this is sum of the object which is graded, and every graded component is finite. Okay, so
Now you see that Z belongs in some homogeneous component. This is expressing some homogeneity.
exactly, this is C star cross C star invariance. Nothing by that. So C star cross C star invariant in the vertical direction, in the C2 direction, just means that the expression must be this way. And so now I kind of say claim for future. So those G S plus 1 T plus 1 are our, I would say, describe the action of the Hodge group. So we will talk about this later, but I just wanted to say that the most important part of the actions is those GST. So
Those coefficients, those constants, S plus T plus 1, S plus T plus 2, are they?
sorry, what?
There are these, those S plus T plus 1, or S plus T plus 2, that simplifies what?
You will see in a second.
It's going to be a very long second.
Doesn't matter. You will see why they appear, but I'm not yet ready to write down to you the answer. So just step by step. So okay, so the curvature of this connection is non-trivial, and in a sense, it's almost everything we wanted to know about the situation. It contains the action, the fiber-wise action of the Hodge group. Now, then the second question was, what is this condition doing here? So those guys, GST, they're just fiber-wise. So fiber-wise, they will define as mixed Hodge structure, but then they have to satisfy the Hodge structure, when we will define it, have to satisfy the Griffiths transversality condition. And this condition is just equivalent to imposing Griffiths transversality. It's not more, not less. It's precisely Griffiths transversality. Yeah. It's later. I mean, it's a statement of the theorem. I can explain why is that. It's the main point is that we will use this connection in order to produce mixed Hodge structure, like 2-3 filtrations and so on. And then the Griffiths transversality condition for this Hodge structure is going to be the same as this condition. It's equivalent to this condition. In particular, this condition is obviously Maurer-Cartan equation, because it tells you that the curvature on some slice of your B cross C2, the curvature restricted to B cross C is flat. And so the curvature restricted to B is flat anyway, because that's anyway, so it's basically one condition, and this condition is obviously a differential equation, nonlinear differential equation. It's Maurer-Cartan type, because it's a curvature equal to 0 condition. Okay, so now I need to define this guy. So let me just say the word. So why do I care about this GST? It's a comment. No, I care about those particular GSTs. Well, the first answer I already explained. They encode mixed Hodge structure, fiber-wise. But the second condition is this, that if you take F, any number field, then there exist analogs, direct analogs of this GST guys for, I mean, for the following specific manifold. So we have to take the hyperbolic 3 space R2 times hyperbolic 2 space R1 time and divide by some actionless discrete group. So, so my main point is that on take instead of GR W pi 1 the cohomology of the space, I can write down the analogs of these GST operators, which will go by almost the same construction. I don't know what their purpose in life, but they come kind of simultaneously with this construction. this is later, so I just wanted to explain that the curvature of this connection is the main player. Now I want to construct this connection. Yes? What?
You will come back and explain this point B later.
Yes.
Okay.
Somehow this is one of the points.
So is this B in this case? Is this going to be our B?
No, this A and B, I don't know. It's just 1 and 2. Sorry, it's kind of it's just numbering. So there's 2 points. Huh? Yeah. All right. So let's construct this connection. Well, so first of all, I was explaining here that all I need to do, I need to construct one form on B cross C2 with values in this Lie algebra. But this is the same as to construct a linear map, which I call the Hodge correlator map, which is going from C Lie star of X to one forms. I just playing around with dualization of maps of vector spaces. What I'm saying here is that to construct a one form with values somewhere is the same thing as a construct map from dual of this somewhere to the space of one forms. And this is the way I'm going to produce this connection, this one form. Okay, still I need some preparation. So first of all, I need to define green functions. I mean, this is basically the construction which I tried to explain briefly last time, but now I'm doing this with care. So first of all, who are the green functions? Green function. First of all, it's not exactly a function. It has singularities. So it's a function of two variables which depend on our tangential base point. And honestly, it's a zero current on x cross x. Actually, even put bars. Okay, x cross x. My fibers are compact by convention here. So I'm going to do this fiber-wise. So I assume now that I just have a curve, not a family. And so I take the diagonal and embed it to x cross x. I'm doing first this construction fiber-wise. And then I'm going to talk about cohomology groups of my curve x bar. So h0 and h1 and h2. And I am going to pick some natural representatives in this vector spaces. One of them is obvious. I can take 1 and multiply it by c if I wanted. This generates h1. This is the function which generates h0. The other, I can take omega 1 plus omega 1 bar. And these guys generate, this is the forms which generate the cohomology groups. So that's very natural. But when I come to h2, there is no natural choice. So what we usually do, we take a metric mu dz bar and declare this representative of the cohomology class, where we usually say that integral of mu over x is 1. But I'm going to use a different choice of this, so to speak, harmonic representative. I'm just going to take the delta function at the point s0 times c. And so these are my, so to speak, harmonic representatives. These are distributions which represent the cohomology classes of h1 of x. And now I can take the identity map on the cohomology and represent it in two different ways in cohomology. So let's consider identity map as a map from the cohomology of x to itself. And then by Poincaré, yes?
Sorry,
delta S0 is not a function, it's a 2-2 form of type 1-1. Why? Because it can be evaluated you can take any test function and pair delta S0 and a test function. Which means it's a functional on linear functions. Which means it's a 2 form, but with generalized coefficients.
Is this the same as just saying the Chern class of point inside of this?
No, Chern, just delta function. So delta function is a way I represent second dimensional cohomology of my space. That's all I'm saying here. And okay. Now I have the identity map from H2 to H2.
Sorry, I didn't understand that. So explain to me again how you think of it as a 2 form.
Okay, so what is a 2 form? So if you have what is a 2 form? You have some form of f of x, y, I don't know, dx, dy on your curve. You can ask what this is, and then the pairing. And then the answer is this is integral f times phi dx dy. Now, instead of taking this guy, I'm taking delta function at S0, but I still can pair this with any function and produce the value of this function at the point S0. Okay? So this is a current. So this delta S0 is this 1-1 current, or at least 2 currents. That's what's important for now. And it's not cohomological to 0 because the pairing between delta S0 and 1 is 1, which is not equal to 0, so it's not a differential of any other current. My curve is compact.
You could use Poincaré, so you don't have to know about differential forms.
So I use currents. I think it's okay. So, all right. So now I have identity map from cohomology to cohomology, and by Poincaré duality, I can think about this as a cohomology class of the product. And so I can take the harmonic representatives. This har x is this guy which I consider here. It's harmonic representatives of the space of cohomology. It lives in currents. So I can take this har x, tensor har x, and write down here a harmonic representative for the diagonal map. So this guy represents the identity class. Okay? All I'm saying that if you consider identity map on the cohomology to cohomology, it defines you a class, the cohomology of x cross x. Okay? And so this cohomology space by Q-knot formula, I can write this as cohomology of x, tensor cohomology of x. But it's canonically identified with my space of harmonic currents, tensor my space of harmonic currents. That's why I was talking about them. Because we identified cohomology and their representatives.
Oh, but don't you mean x bar?
X bar everywhere, yes. Thank you. Okay? I can just write down some formula for that, but I explain what's the meaning of this. So we write down the identity operator as a certain harmonic form on x cross x. If you would have something nicer than this delta function for harmonic forms, probably nobody would object. We just write down harmonic representative. But I take this definition of what is harmonic. But on the other hand, there is this delta, there's diagonal, so there's delta function of the diagonal, which represents the same cohomology class. Okay? So I can write down this class, the identity class, in 2 different ways. I can either write down the delta function of the diagonal, which gives me this identity map, or I can write down this as a harmonic form. Okay? If you want it, I can just write down this concretely, what this H delta is. So this is something like 1 tensor delta S0 plus delta S0 tensor 1 minus square root of minus 1 over 2 sum k goes from 1 to g of, I choose some basis in the harmonic forms, are called alpha k and alpha k bar, and minus alpha k bar tensor alpha k. So, and these alphas are normalized in such a way that integral of alpha p wedge alpha q bar is delta pq over this curve. So this is a concrete, I just wrote down what I said in the basis, so to speak. All right. That's okay?
Yes.
Okay. So now I can try to solve the equation. I can try to say that I consider equation d bar d of this green function xy equals delta function of the diagonal minus this harmonic form. And because the right-hand side is cohomological to 0, so this equation has a solution. And so this is this solution is the green function I'm going to talk about. The solution of this differential equation. Huh?
Where does V0 come into it?
Good point. Now in a second. And now the second is a second. So normalized, very good, Richard, so it cannot be better. Normalized as follows. Huh? What?
You can solve it because you have what you say, and also it is of type
Sorry, what?
You need that this delta delta minus harmonic is of type
It is of correct type.
correct type.
Yes. You see it's type 1, 1. Yes. You're right. So it's, but this is a correct type, and so yeah. So okay. It took longer than a second, but still. So it's normalized by V0 as follows. So I take t, a local parameter at the point S0, and it is normalized in such a way that dt V0 is 1. That's normalization of this local parameter. That's why V0 matters. And then the condition is that this g V0 of xy minus logarithm of absolute value of t. What does mean logarithm value of t? So first of all, this is S0. This is a function of y. So if I take this function of y, then it vanishes at y equals S0. So what this formula says, that it says that the green function has singularity near S0. And this singularity is log t. But you can always add to green function a constant. So how you normalize this constant? You normalize this by the condition that this log t not only gives singularity, it also gives you the constant terms. This difference is 0. So then it's uniquely defined. Okay? All right, so one can have example of this.
So this har x is what you call h delta up there.
No, h delta is element of har x tensor har x.
But you wrote on the DD bar line, you wrote a har x word.
Oh, thank you very much. I didn't mean this. Yes. It's h delta. Yes. I mean this. Yes, of course. I'm talking about representative of the diagonal. Yes. Thank you. So example, so if you take CP1, then it comes with coordinate z. And so you take S0 to be 0, and you can take V0 to be d over dz. And then your function will be 1 over 2 pi I logarithm of z minus w. Okay, so we have the green function. Now we need to write down, so to speak, the. Okay, so I have time to about 3 o'clock, right? So because there's no t anyway yet. And then I'll stop. So now this one form I'm talking about will be given by this integrals related to trees, which is kind of Feynman integrals. And so in order to do this, first of all, we need to draw a picture. So how we define this connection G. So we take this graph. It's a plane trivalent tree. And so we take, so once again, T is a plane trivalent tree decorated by our cyclic word. So we have a cyclic word W, and the cyclic tensor product of associate graded of H1 of X. And so because it's associate graded, can be written naturally as a direct sum of two components. So S star is S minus distinguished point S0. So direct sum with the cohomology of the compact curve, which is holomorphic differentials plus anti-holomorphic differentials. So when I take cyclic tensor product of those guys, I can just mark them in the following fashion. Like this is point S1, another point S2. This is some anti-holomorphic differential alpha 3, some differential alpha 4, just an example. Maybe S5, alpha 6, and so on. So this picture, it tells you that you have a tree T, and this tree is decorated by the guy. And so remember that our goal is that we want to assign to this guy a number. Actually, not a number, one form. OK, so the next thing, one form where. So
So those S are element of S minus S0. But
yes.
where are the omega 1,
So alphas, they belong to here.
Oh, I cannot this.
Ah.
Okay, we have some alphas and some and I did not read.
Every external vertex is decorated either by differential one form or by a point. So that's the data.
You did not have some rule that 2 powers don't follow each other?
What rule?
You did not have some rule you want?
No rules.
No rule.
No rules. No rules. So just any collection like that. So for example, all of them can be S, all of them can be alpha, no conditions. OK, now we want to define a form. About to finish the first part. So what's the goal? So I want to define a form on some space. So let me introduce the space first. So I consider X sub t to be product of x's over the base raised to power given by all vertices of this graph T. So this is the fibered product of this guy. So for example, in this case, so it's x over b raised to power 10. This is my x sub t on this particular diagram. 10 is total number of all vertices. And so I wanted to have form on x sub t cross C2. And then I want this form to be current integrable. I said one form? No. I want a form. Sorry, it was a mistake. So form has name. It's kappa T of W. And then I'm going to push it down to B tensor C2. And the push down, the direct image is going to be the form I'm looking for. So there's an
All vertices are the inner one as well as
yes.
the one on the surface.
Yes, x to 10 in this particular picture. And so this has natural projection to the base.
Sorry, where did this tree come from?
What?
Where did the tree come from? In terms of what you're still trying to define for us this form.
Yes, I want to define a differential form. How I define this differential form? I define this differential form as an integral of some other form, big form. It's called form kappa. So I'm going to define the big form, which is big form on this space. And then I'm going to integrate this form over x as parameterized by the vertices. You'll see how exactly when I'm going to the construction. And so in the end of the day, when I integrate it out, I get the one form I'm looking for. Sum of all possible trees, yes. Yes. So this is I mean, there is no physics here whatsoever, but this is a kind of Feynman integral. So what Feynman integral always does, it tells you what kind of graphs you consider, in this case plane trivalent. It tells you what kind of things you do at the vertex. Well, first of all, it tells you what do you put on the edge. Secondly, it tells you what do you put to the external vertices, and it tells you what do you do at the vertex. And then it tells the sum of all possibilities of all possible graphs which are of this particular combinatorial type with this particular local data of three types: edge, vertex, external vertex. This kinetic term, potential energy, and the insertions. So it has this shape. I mean, I'm not talking about Feynman integrals, but it has this shape. Okay. All right, so probably I stop here. It's 3 o'clock. So when I come back, I'll write it down.
When are you coming back?
It depends on.
3:15?
3:15 is fine. So I think I have permission to continue. Okay. So I need to define now the rules. So again, the point is that I want to construct some differential form of big degrees. Big degree on this guy and then integrate it down. Now, first of all, some notation. So remind you that we have twistor plane and the coordinates there are z and w. So we have on xt we have the RAM differential, and I'm going to write it down as usually as d plus d bar. So this is notation for what is d and what is d bar. It's on xt. And most importantly, differential operator, which magically makes things work nicely and simply. So it's the following one: omega d minus z d bar plus z dw minus w dz. So now, where is this differential operator? It's on xt. You remember xt is this big fibered product over vertices cross C2, cross the twistor plane. Now, is that okay? Let's just set. So
You mean dw or del w?
no, I mean this is d. I'm not sure I see. What's the question?
What's this on?
It goes from where to
It's a differential operator where? It's a differential operator on xt cross C2. So you have zw variables and also d bar operator and d.
function is mapped
To one form. It's yes, to one forms. Yes. But this twistor plane and d and w, they are mixed. Is that clear now? Okay. Now, to each edge E of t, we assign a certain current. Yes?
Sure, it's clear to me. So what's the thing you've written as partial?
Okay, so you have, first of all, you have a complex manifold. So you start with a complex manifold with your curve. Then you take, it's a curve in a family. So it's a big complex manifold, fibered with fiber curve. Then you take this complex manifold and you take its product with itself over base many times. You still get a complex manifold. It's denoted by x sub t. Now, next sub t as on any complex manifold, there is d operator and d bar operator. Their sum is the de Rham differential operator d. It's a
So it's infinity function to
yeah. So d x from c infinity functions on xt to c infinity 1 forms on I said xt, yes, xt, and d bar x from c infinity function on xt to 0, 1 forms on xt. This is just d is sum over d over dzi, dzi. It's a usual notation. So you use local coordinates, holomorphic coordinates, then you write now this is this way, and d bar is sum over d over dzi bar, dzi bar. And if you take sum of this, you get the usual differential. D plus d bar is sum over d over dxi, dxi plus d over dyi, dyi. Okay? So this is d and d bar. Can I erase this?
Yes.
Mm-hmm. Okay, so now we want a current. First of all, this current will be denoted G sub E, green function, tilde, and it's a current where on X cross C2. So it's a current on X cross twistor plane. Yes. 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 G tilde by definition, so it has 3 different flavors. So the first flavor, I beg your pardon, can I erase this? Just this, because I need more space. Is that like everybody wrote this?
But is it true? Is it still correct?
Huh? Ah! Now let's erase it anyway. Okay, so what I wanted to do, I want to say that I have edges of 3 different types. It could be just an edge, which is external edge, like that, and it was decorated by alpha and has little variable x, which is a running variable on this vertex. Or it could be edge, which is again decorated, but now by s. Or it could be general internal edge, and then it looks like that, x and y. So to each of these cases, we're going to construct some current. And so in this case, this is the most kind of typical case, we take dc of the green function on xy. Now, I hope this is clear. So I have a green function which was defined before. So this E, it's just a green function. Okay, so I should write down P sub E is a map from x sub t to x cross xb, which corresponds to this particular HE. And here you have the function, the green function I was talking about all before. Now you just pull it back, and you say that this GE is just pull back of this function to this big space. Okay? I also need to and if you want it, I can put here C2, but the function is just there. Okay? So if this is clear, this is good. So this is a little non-trivial plane. So you have the green function, it's a function on xt, but you apply to this differential operator. So as an output, you get a one form which no longer lives on xt. It has some components on C2 and some components on xt with coefficients z and w. It's kind of mixed form. Now the other ones is the following. So here put delta function of the diagonal times alpha, and here put again this dc green function of xy multiplied by delta s. So it's kind of y here. Okay? So in simple terms, what I'm doing when I see this tree, I mean, I gave you a formal definition, but there are really edges of three different types. There are the kind of edges where I put green functions differentiated by dc, these edges. Then there are edges where I put alphas like these edges. And then there are some other edges where you put the delta functions. Okay? And so
So when you write alpha, it's sort of alpha pulled back from delta.
yes. Alpha is a differential form on my x.
Yeah, and you put it back from the thing labeled by.
Yes. It always has this notation that you pull back from the things labeled by the external vertex. Yes. Okay, so now I have these forms. So
Sorry, and then what's delta?
delta s is a delta function. So you have here you have product of curves x and y is a product of two curves. On one of this curve, you can put delta function at s. It's a 1-1 current.
No, I meant, okay.
But you can still multiply it by the green function. You still have
What's delta of x though?
what?
Delta x in the.
Oh, delta x is the delta function of the diagonal. Maybe, I don't know how to. Maybe I should denote this delta delta.
And the diagonal corresponding to the two copies.
Yes. So you have here two copies of x and y. You have here this x cross this x, and then there is a diagonal here sitting here. And so I put delta function as a diagonal. This delta function is just delta function as a point. Okay? Okay? So again, all I'm doing, I'm putting some distributions on the edges, and then then comes the main definition. So let's put it here. Okay, still.
What sort of object is G
Hmm?
tilde? What sort of object is G tilde? It's
Who tilde?
GE tilde.
It's a current on x cross x of degree 3.
Well, x on xt.
No, it's okay. It's originally current on x cross x, which was pulled back trivially then on xt and cross c square. So this guy, I believe this is what I wrote down here exactly. So this gi is a form on x cross x over b cross c2, then pulled back to the big space. So its main point is that it's defined locally here, and then you pull it to the space xt cross c2.
I assume that these choices make sense with respect to some combinatorial structure on the set of all T that you haven't.
I don't.
Why are these the best choices for this?
This question I cannot answer.
But you chose them,
Yes.
and you don't know why.
No.
I don't believe you.
No. I'm very sorry. I don't know why this formula works. I know.
It works in first what?
Huh? They will deliver the Hodge structure. You ask me questions. Why it's a play?
They solve some equation.
Maybe we wait a little bit later when you will see the properties of this combinatorial data, because I'm not even able to tell you what you will see. All the properties. You will see y trivial entry, y plane trees, y trivial entries, and so on a little later. But I'm not sure I'm answering your question. But let's just wait a little bit.
So
Okay.
sorry, the purpose of all this is to define that one form.
Yes.
Is the purpose of the one form G to deliver these GPQs?
Yes. And Hodge structure. The form G, as soon as form G is constructed, you already have GPQ because it's just a curvature of G.
Yes. And the Hodge structure on what?
Hodge structure on the pi 1 of x in the end of the day.
Ah.
Yeah.
So how should I in the middle expression for G tilde?
It doesn't matter. So you can put it this way. It doesn't matter, but you're right. So you put it this way.
You said this is a 3 current?
3 current because this is 2 current. Okay. Okay. So wait. This one is just a function, and so this is just a 1 current. So this one is this is 3 current. This is 3 current. It depends whether you're inside or outside. All right. Let me write down the main. Yeah.
Also, travel and tree, just one line across the circle.
Sorry.
With no inner vertex.
Sorry. Once again.
I was wondering when T is just one edge going from a part outside to another part outside.
This makes sense. This one
Yes.
makes sense. It's actually what to do.
Tell what we do.
I can tell you what to do, but what if I tell you what I do a little later when this will play a major role? Because this gives a connection over the base. So, okay. So, okay. So let's just make the definition. So we consider the set of edges U0.
Sorry, Sasha, when one's considering all these possible graphs T,
Yes.
do they have to be connected?
No. Yes. Sorry. Yes. I mean yes and no. So you can take it. You can take the sum over connected trees, or you can opt to take the sum over disconnected trees. Then there is a theorem that the sum over disconnected trees is exponent of the sum of the connected trees. So let's just make it over connected trees, but I'm saying that you can do both, but they give you the same information.
Doesn't make much difference.
Huh?
You say it doesn't make much difference.
I mean, one is expressed through the other.
No.
So I take the sum over connected, but yeah. Okay, so let's take the sum over all edges. Sorry, let's take the collection of all edges. This is all edges of T. And now I write down the main here. So this is a differential form which is going to be integrated. So I call it kappa T of W. And so this is the following. So first of all, I put some sign, which I'm going to explain in a minute, because I choose some order of the edges. And then I just take the wedge product of all these differential forms. So this is the main hero. So all I said that I take the wedge product of all these forms with certain sign. Now, what is the sign? So first of all, these GIs are of odd degree. Now it's important. And so whenever you interchange 2, you pick up the sign. Therefore, in order to make sense of the signs I need to have the following little nice combinatorial lemma, which says that trivalent trees, plain trivalent trees, have canonical orientation. It's a lemma. There exists canonical orientation. What orientation means, I'll tell in a second. Of the set of the edges that is an order. And now I'm telling you what orientation of a set is. An order modulo even permutations. So if you have a set, orientation on the set is a choice of enumeration of this, ordering of this set, modulo even permutations. And so I claim that the set of vertices of a plane trivalent tree has a canonical orientation. Now, where is this orientation? Maybe I can still do it here. So first of all, example. So if you have plane trivalent tree like that, you can number it like that, or you can number it like that. Obviously, the permutation is even. Secondly, if you consider more complicated tree, I use orientation of the plane as an input. So if you have a more complicated tree like that, So now let me define you the orientation of this tree. So you start, you pick your favorite edge, this one, and you,
I don't even understand this, just these three things.
so okay, so we have a set of all edges.
Yeah.
So an orientation of a set is a choice of order of the set, modulo even permutation.
Yeah. Why
So-
can't I just change the numbering of 2 and 3?
No, I use the fact that that it's a plane graph, so there's a cyclic order of external edges.
Would the external edges ordered cyclically?
Yes, and so I use, and they order it clockwise. I use the fact that the plane is oriented. We are answering some of the questions of Michael, I think, here. What properties of the graph I use here? This one. It's plane, so plane has orientation. But we are not yet done, so let me take this graph and draw here a similar copy here. Now, if you can try to do the orientational graph as follows. You choose a vertex number 1, then not vertex, edge number 2, then number 3. Here you don't do anything because you already counted this edge. This is number 4. Here you don't do anything because you already counted them. This is number 5. Don't do anything. So I produce an order of the edges of this graph. So what I do, I take any edge and travel around and mark the edges which didn't come yet to my attention. Okay? So let's do this one step to the right. So we start here. One, 2, 3, 4, 5, 6, 7. So what's the difference? The only difference is that we shift. So on this kind of tail, we shift the numeration by 1. Okay, but it doesn't matter because every plane trivial graph it has odd number of edges, and so shifting by 1 is okay. It's even permutation. So I just proved that any plane trivial tree has canonical orientation. Is that clear? I mean, is it clear?
See the example.
Huh?
I understand in the example.
The example gives you the proof because let's prove this carefully. So if you started here and go here, the only thing which happens is that this guy, which was oriented in the beginning, now is going to be oriented in the end. Other than that, the pattern is exactly the same, right?
Yes,
Huh?
but it's not always so.
It always so. Because
You get this rule that if you have already met somebody, you don't mark it. So when this
no, it always, because you started here and you go into part of your tree which grows here, and then it's like you start fresh. So you make your rule starting here.
but start with 3, for instance.
You first of all you start with 2 and prove that it's the same. Then start with 3 and prove that it's the same with respect to 2. So each time when you move by a step, you use a even permutation. By
Are you claiming that there's a canonical
Absolutely.
order of the vertex?
Not the cyclic order, canonical orientation of the set of internal edges. And I'm
This example is moved by a 5 cycle as he did this.
yes, it's always an odd cycle. That's the point.
I hear that claim, yeah.
Why is this so? Because if you try to make one more, I mean, this is the claim that any plane trivial tree has odd number of edges.
So somehow every edge sort of, you started at 1 and then you went around till you ignored 1 and you're taking that subgraph. And
Yes, that's exactly the argument. So the argument is this: so you start your favorite edge where you started, and then you're going in this subgraph and see what happens. The rest doesn't play a role because nothing happens in the rest. The rest will be as before. Nothing happens there. And so when you do the shift by 1 on this 5-edge graph, so you use the fact that number of edges is odd. So this gives a proof. This is important because otherwise the construction would be empty. Because what I need to do, I need to assign a sign here, and by definition the sign of E0 and so on, E to M, is this. So you take, I mean, you take your orientation given by this order, and you kind of divide this by canonical orientation. Divide means that your orientation forms a Z mod 2Z torsor. So for any two of them, you can tell the difference, which is a sign. So that's the definition of this sign. And that's it, because this definition of the sign is consistent with the fact that you have here wedge product. So the point is that you get a well-defined form, which does not depend on any choices, although it looks like it depends on these choices of signs and so on. All right.
And this is a current of what degree?
What? Current of what degree? We will count this in a second. So first of all, the main statement is that this is a current. So this is, in a sense, one of the key steps in the proof, and this is not at all obvious. The statement is that the kappa T of W is integrable. It's a non-trivial fact. Not at all trivial, because what you do, you work with forms with singularities over the diagonal. Then you start multiplying them. It's already a little illegal. But then you have to trace what happens when a collection of points collide together. It's a quite singular current, but the theorem is that, yes, it's a quite singular form, but the theorem is that it doesn't have singularities. Sorry, that it has only integrable singularities. Okay? I'm not talking about proof of this, so I can, but right now I don't.
So that's the integrability that lets us integrate it along.
Yes, 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 yes. Now, therefore, we can make the definition. So we define the correlate.
So what were you saying? Yes, 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 yes to? Where is kappa T of W?
Huh?
On what does kappa T of W live?
W is a decoration by S and alpha.
Yes.
Where is what?
So you're saying it's a current on what?
It's a current on x sub t cross c square. It's obviously non-singular on c square, but it's integrable on x sub t. Okay? So I use here crucially the fact that logarithm of r is integrable function on c. That's one of the things, and some other things. All right, so now I define the Hodge correlator of this W to be the sum over all plane 3-valent trees connected, decorated by W. I mean W.
W is also one of the coordinates of C2.
Huh?
W is also a coordinate of C2.
No, 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 no. Oh, you mean?
It's a big W. Oh, I see. I can't. Okay, that's much better.
Okay. Actually, you're right. So yeah. Okay, okay. So let's make a definition. So the main point is that you take this current, which is integrable, and you integrate this over fibers of this map. So you have a map from x sub t cross C2 to b cross C2. And you just integrate. So this integral and sign underneath means that you take push forward of this distribution. If you have a distribution, you can always take a push forward. So then you divide this by some normalizing coefficient. And that's it. So that's the definition. Okay? Now, the next claim is the answer to Richard's question. So the claim is that the current I get downstairs is a one form. Now, I'm going to check this in some particular case when there are no s's, but there are only alpha. So you see how exactly the combinatorics works, and then you can do exercise in general. So, sorry, what?
But there is no singularity.
There are singularities. There are green function has singularity, but they're integrable.
But yes, but on beta.
We could have. I mean, it depends. So we get a current. I mean, we get the currents there. So a push forward of a current is a current. We certainly can have singularity, and we do have singularities, but they're integral. That's the only. Okay, so let's just make a check about the degrees. Because actually, it's this check will play a significant role when I go to number fields. So let's just take some example. And let's suppose we have only one forms. So let's suppose that we have E is a number of edges. Edges, I mean internal edges. Then you can easily see that E plus 1 is a number of internal vertices, and that E plus 3 is a number of external legs. This is a little exercise about trees. So trees always have this property. Okay? Legs. So this is legs. We have 6 legs in the case when we have 3 internal edges. So now how the integration goes. So first of all, in the integrand, when I say that we have, on that formula, we have delta, did it disappear? On alpha labeled leg, we have delta functions times alpha. But this in simple terms means that we just put these alphas at those axes which sit here. So this means that we have already a differential form of degree E plus 3. It comes from the alphas, from outside. Okay? And it sits here. Now, then green guys, they are one form, so we have E of them. And now we subtract the integration cycle, which is this one. So we end up with a number 1. So this is dimension of x2 internal vertices, and this is form given by alphas, and this is the guy which is given by CGE. So it's a one form. Okay?
I'm afraid I haven't followed.
Okay, let's do it again. So good. So we consider a particular case. We consider a particular case when the tree is decorated only by one forms. No.
So well, maybe I could ask you. You've taken away 2e plus 1.
Why taking away 2e plus 1? That's the question. Because I integrate, I already, integration of external vertices already incorporated in this picture, because I integrate over diagonals to pull it down to here. Then I still have to integrate over x raised to power given by number of internal vertices. The dimension of this is precisely 2, which is the real dimension of the curve, multiplied by the number of vertices, which is e plus 1. Okay? So I emphasize that in this construction doesn't look algebraic geometric, because what you do, you integrate a differential form which constructed from green functions over the fundamental class of the manifold. It's not what we usually do in algebraic geometry. We take holomorphic forms over cycles, but not like that. Okay, so if this is okay, I'm going to now to proceed to examples and. Richard, is it okay, or
I didn't follow it, but I can
oh, okay. Let's do again. let's do again. So what's the integrand? The integrand has contribution from alphas, and we have as many of them as the number of legs.
Yes.
This is e plus 3.
And but you've done some integration already. I mean,
I already
I
so
would have thought it was
let's go.
3 plus 3.
Let's go. What?
I would have thought it was 3 e plus 3.
No. I said, but
You've done some
I did some integration because I have delta function multiplied by alpha, and I integrated over external vertices. So this delta function is eaten by this integration, and alpha travels to the internal vertex. So I do integration over external vertices, and the effect that they pull all the alphas to internal curves. Okay. So now the integral is simple. So you just have alpha sitting on the corresponding curves, and then you have dc of the green currents on the internal edges. Okay.
Yes.
And so now e plus 3 is explained. E is each internal edge has dc of the green function,
Yes.
which is one form.
Yes.
And we have e of them. So we have e plus 3 plus e, which is degree of the differential form.
Yes.
Then we integrate over 2 times the number of vertices. So we get 1.
Okay.
And I claim that the same will happen in general, but I don't want to do this on the blackboard. Okay?
Okay.
Okay. So it's always one form as was promised. Okay, now let's do some examples. By the way, this is the form. So this is the form which was promised. So I promised to here to construct the one form on B cross C2. This is the form. So the job is done in this sense. That I produced a form here, which is a one form with values in this Lie algebra by definition, because we constructed it dually. We took the dual of this Lie algebra as this W and constructed one form here. The same thing. So we constructed one form, and you can see by very definition that C star cross C star equivariant. It's part of the game, but
Not completely to the wrong because you did not prove the Saffold relation.
yeah, you're right. But I'm not. It's a shuffle relation is something from the geometry of plane trivial trees. I can do this maybe next time, but I prefer to. It's a little bit too much combinatorics, I think. So let's just not do it. Okay, you're right. So I didn't prove shuffle relations, but it's automatic. As soon as you take sum of plane trivial trees of anything, you'll get shuffle relations. This is one of the reasons they're so good here. Okay. Uh-oh. I'm going slowly. So, okay. So what happens if you take this decoration? This answers Pierre's question. So, for example, this one. So what this diagram tells us? So it tells us the following, that we have a section from B to X, and then we pull back the one form using this section. And so this is the one form on the base. You can cross it out by C2, so it does not depend on the twistor parameters. So that's what you assign to this diagram by definition. So if you look at the definition, it tells you exactly this. So it is this case. It is which case? I think it.
I think you only wrote Caesar and there was one in interior. But
Yeah, I think I didn't write this case, but this is the definition of this case. No, actually it is. So okay, let me do it since I actually prepared this at home. So you take delta function of x minus y. I think this is overkill to do it over the blackboard, but let's do it. Delta s times alpha. So I'm doing this integral over external edges, and so over x cross x, because it's a delta function which is on one side. I should admit that I didn't put this in definition, but anyway, this is a rule. So it gives you integral of x. If you do this, then this is the same as a pullback of alpha. So
if you look at on your left board, E
is minus 1, is that correct?
What?
Look on your left.
Yes?
E is minus 1 here.
E? Its number of internal edges is 3. You're talking about this E?
Oh, this one.
Sorry, I don't.
How many internal edges are there in this example?
None.
He's asking how
None.
many internal
I
Huh?
see minus 1.
None. Anyway, so you can. This is it's a special case in any case. So now let's consider. In all other cases, you do have internal vertices at least. So for example, you can have this one, alpha 1, alpha 2, alpha 3. Then you have some variable x here. And you end up with integral of alpha 1, which alpha 2, which alpha 3 over x sitting over b. And this is again one form because you integrate 3 form over 2 cycles. So one form over the base. Okay? So, and one more example. All these examples are kind of important for me. So what happens if you put, this is example we tried to consider last time, S1 and S2. That's another example when you can have no internal edges. So in this case, the rule tells you dc with respect to S1, S2 variables, the dc of g of S1 and S2. So it's one form like that. Okay, so and maybe one more example. Yes.
So this example 2, is this xt or something that you're xt to be?
It's my xt in this. So what I'm saying is that I already did integration over external vertices as usual. So I pull them here, and then I just get 3 forms on x, and so I just integrate the product over x. Okay? So the integral is just simple as that. I always tend to do integration of external vertices first. Okay, one more example. That's where it already looks like Rankin-Silberg integral. So 3, let's do 4. So let's take one s variable here, one s, and alpha and beta here. So what do we get in this case? So in this case, we get dc of the following guy. Take integral over x to b of g s x alpha h beta. So if you have no base, then it's also the dc still makes sense. The dc just multiplies this by one form zdw means wdz. But if you have full base, then this is even more non-trivial operator. But the main point of this that you have to start with this integral. You have to integrate green function wedge with 2 one forms. And if you do this on the modular curve, as we discussed last time, you recognize that this is one of the Rankin-Silberg integrals. Okay? If you do another one, so I stop here by doing examples like this. So you have, if you put 2 S1 and 1 alpha, then the integral will be, again, the main part of the integral will be g of S1x dc g of S2x minus g of S2x dc g of S1x, which alpha, this is a Rankin-Silberg integral, and you still have to differentiate at dc.
I guess this makes sense if S is a cusp.
Yes. If you have a modular curve and if your s's are at cusps, that's what we discussed last time, then the green function turns out to be, by Kronecker limit formula, for example, it turns out to be the Eisenstein series, and therefore, and alpha and beta are cusp forms. We take them cusp forms. Then this is precisely what Rankin-Silberg integral looks like. Okay. All right. But what do we have in general? So the point which I wanted to say is that the functions which we get here from simple diagrams are basically green functions, or these integrals which are like regulator integrals.
Well, it's all things on b equal back to b times c squared.
Sorry, what? This is all considered. So this is considered as something on b cross c2.
But you first get it on b and then you take
I take a pullback, yes. So I don't write it, but yes. Now, the claim that we always get the form G in this form. We get something, I can call it, G plus the following sum. So the claim is that in the end of the day, the one form which I constructed is always can be expressed through some functions GST, which already appeared before as a curvature.
What's the sum of what little s and little t are we summing?
Oh yeah, good point. St bigger or equal to 0. So the claim is that basically by the very definition, the one form G which I'm getting is some little g which I didn't discuss yet, but the rest lives on b cross C2, and it's given by its main input is some function on B and some one form on b cross C2. But it all comes from G. So this G, which is, remind you, is a curvature in the vertical direction, interpreted later on as a green operator, it tells you the whole connection which we get. So in this case, this is true basically by definition. So you decipher this definition of wedge products, and you see that you get this. It's a little calculation, but really little. So it's basically by definition.
Sorry, but what's the justification for the indices? This is the homogeneity in the
Yes. So the main point is, first of all, Michael's point. So Michael asked where does this s plus t plus 1 comes from. It makes this coefficients 1. Number one. Secondly, why this is s plus 1, t plus 1? Because degree in z and w is precisely s plus 1 and t plus 1. This form is on the nose homogeneous. C star homogeneous. And this form is also on the nose C star homogeneous. If you remember about the weights in the Dolbeau complex, they also have weights. So this form is homogeneous by definition. Now this guy G is a very simple thing. It's just the sum of two diagrams which I already defined. And this is just a one form on B. And the rest is forms on B cross C. So I can probably write down you G11 just for fun now. G11 is given by the following sum of diagrams. So S1, S2 plus.
What's s in the definition of little g?
We have S is the definition of, sorry.
In the definition of little g.
Little g is it's a one form on B. But the base B has S's sort of as a part of the data because we have sections from B to X all the time. They're called SI.
Yeah, which one is it? The s you put?
All of them. All of them.
So the sum of all.
Yes, some of them. Yes. So all S from S star. I don't want to write sum too much here because if you have to take sum, so this makes sense. But just not do this because the diagrams get polluted by too many indices. I just writing down one example. What it So if you want to write down G11, then you have to consider some like that. So this is, here the sum of plane trivial entries already appeared, and so on. Okay?
I can't read what can't read all the labels of them.
I mean, I'm saying that I put here, okay, I try to run this quickly. So I put here 2 S's. Here I put 1 S and 2 alphas. I call them maybe alpha 1 and alpha 2. And here I put many alphas. 4 alphas. Okay? If you want to get non-trivial integral, this has to be holomorphic, anti-holomorphic, holomorphic, anti-holomorphic, or other way around. Otherwise, the integral obviously 0. So, but you may or may not say this.
So in the definition of G, we're all alpha 1, alpha 2, and alpha 3 holomorphic?
Yes. Yes. I mean, not holomorphic, anti-holomorphic or holomorphic. All right. Now let me do, I still have maybe like 5 minutes, I believe. So I wanted to do the fun exercise is actually to prove that this connection satisfies the condition that it's flat. This is where you see how all this plays together. This is on this line, yes, yes. The first question, why on this line? Because there is the following identity which makes it true. I'm going to give you basically complete argument and in 5 minutes. So of which is the same thing as Maurer-Cartan equation. The first thing, let me just introduce notation. So I have my one form, and I restrict it to z plus w equal to 1. So I call it maybe g prime. Okay? Then I can parameterize this line, writing that z is 1 minus u and w is u. So basically, I have just one parameter on this line. And it turns out that if you check that d plus this du applied to my form g prime, so what I want to prove that I have this equation. That's what I wanted to prove. So the key fact which is responsible for the fact that the proof works easily is that if you take differential plus du and apply to this funny differential dc, again restricted to u, you get just d bar d. This is the reason this dc appeared everywhere. So it plays the same role. I mean, usually you have formula that ddc is d bar d. And so I claim that a similar formula is true when you incorporate twistor line. And it's easy check. But if you do on the whole twistor line, this is very much not true. This is true only on z plus w equal to 1. OK? Now, how are we going to use this? So what are we actually going to prove? So instead of proving this, this is equivalent to some dual statement.
So what's capital D lower u upper c?
So remember that we have z plus w equal to 1. So I parameterize this line by parameter u.
Yeah.
And so before we had this d is a Gauss-Manin d. And this before was dc2. Now if you restrict this to z plus w equal to 1, I call it d sub u. Because you take differential only with respect to
Yes.
this direction.
What was the capital du?
Oh, this was not from my notes, but wasn't in. No, it is d restricted to z plus w equal to 1. Whenever I put sub u means I restrict. But this is the dd bar on your manifold x, xt. Okay? So now how this identity is used. So in order to prove this, it's equivalent to do the following. It's equivalent to prove d plus du of this correlator applied to some word equals plus correlator wedge correlator applied to the coproduct of this W. So this delta is mapped from Lie star to wedge square of Lie star. This is just a dual form for the equation. So instead of proving the equation in the Lie algebra, I can prove its analog. I dualize it. It's the same thing. So I'm going to prove this. Okay, now how? Let's. So I have my tree. And so remember that this tree, I'm proving that the connection is flat on this line. And it's equivalent. So this statement that this G satisfies Maurer-Cartan equation is.
There's no equation in the second box.
Oh, just I didn't put 0 here. So flatness is equivalent to Maurer-Cartan equation, which is equivalent to this statement. So all I need to do, I need to differentiate. In order to differentiate it downstairs, I need to differentiate it upstairs, because this is push forward of the currents. It commutes with the differential. How it differentiates the current here? So imagine that I have some edge here, E. So I have to differentiate contribution from each edge. I have to justify this by doing some analysis, but I'm skipping this, just giving you the formal argument. So you take some edge, looks like that. And so you put on this edge, originally you put on this edge dc green function of xy. Now what we're supposed to do, we're supposed to differentiate this. Okay? But this is due to this beautiful identity, the same thing as d bar d of the green function. Okay? But d bar d of the green function is satisfies the green function equation. So this is the same as a delta function minus this harmonic term. And so the output is that when I differentiate anything sitting on this green edge, I'm getting two contributions, delta function and the harmonic contribution. Okay? Is that clear? Okay? Yes. Now I have to take care of two terms. I have to, now I'm proving the following. I'm proving that the contribution of this term is 0. Why it's 0? Because it's a nice argument with orientations. Every edge inside comes twice. So you have four vertices like that. And it comes this way, or it comes this way. So you either have to take delta function when these 2 points collide, or when this 2 point collides. When these two collide, you get this graph. You have here like alpha 1, alpha 2, alpha 3, alpha 4. You have alpha 1, alpha 2, alpha 3, alpha 4. Here you get the same. Alpha 2, alpha 3, alpha 4, but with a different sign. And so they canceled. You need to check that the sign is different, but I gave you definition of the orientation sign, and so you check that if you apply this definition, that they canceled. Okay, so this term is gone. It's gone only because we took the sum of all plane trivial entries. Otherwise, it wouldn't be gone. And the second term is a coproduct, because the second term is simply what you do here. You just cut this. So you put some form on the product two curves. And so you just cut the edge, but that's exactly the operation of the coproduct. That's it. Theorem proved. So the contribution of the differentiation of the edge, there are two contributions. One of them is the delta function of the diagonal, which is gone because we took. And the second is that when you differentiate green function, you get the contribution from the Casimir terms. But this contribution, the Casimir term is a product like harmonic function here and other harmonic functions there. Remember, this Casimir term is identity written in terms of the harmonic functions. But I'm claiming that if you look at this definition, at least the contribution of one forms is exactly what the coproduct was telling us. This is how I define the coproduct in this Lie. There was this Lie algebra, C Lie star, which comes with a coproduct. And I told you last time the definition of the products, that when you glue the things, when you define the coproduct, you cut them. So if I talk for the third time, I will remind this, but because that's important for what follow next. But I'm saying that by essentially very definition, this term will contribute, will be exactly what we're looking for, the coproduct. Then use the fact again that you take sum of all plan-trivial entries, and you get G cross this plus G cross G equal to 0. So what I'm saying is that the proof of this curvature equal 0 equation is basically very simple after you set the integral and use this basic formula and the fact that you have currents that you can play the game. Okay.
You see, you've got the 3 and you put alpha and alpha there, but
Yes.
also you put 1 and delta.
Yeah, you have to take care of this, yes. But yes. But what I'm saying is that originally you start with cyclic word and you produce 2 cyclic words, like this and like this. But they're good because you have to take some here and some here. Okay.